Hello, everyone. Welcome to a new Can seminar lecture. And today I have the great pleasure of introducing Dr. Elgin Guler. Dr. Guler is currently an assistant professor in the Department of Civil and Environmental Engineering in Pennsylvania State University. And her main research interests focus on multimodal urban traffic operations and control, intelligent transportation system, connected and autonomous vehicles, and infrastructure management. She received her bachelor's degree from Bogazici University, hope I'm pronouncing it right, in Istanbul, Turkey, in civil and environmental engineering and industrial engineering. And she also received her master's and PhD from the University of California, Berkeley. And after completing her PhD, she served as a postdoctoral scholar in the Institute of Transportation Systems and Planning in Zurich, Switzerland. Today, Dr. Guler will be discussing signal timing in a connected vehicle environment. As usual, for those of you who have come on these presentations before, we'll have a 40-minute presentation followed by a 20-minute discussion or question and answers, and you will have two options. You can put them on the chat, and we can make them on your behalf, and you can also use the option to raise your hand and have yourself do the question directly. And then, so without further ado, Dr. Elgin Guler, everyone. Thank you.
Thanks, Jesus. Thanks for the introduction there. So as was introduced, my name is Elgin Guler. I'm an assistant professor at Penn State, and today I'll be talking about a flexible signal phasing and timing plan in a connected environment. So this is work that was basically done by my recently graduated PhD student, Joyce Liang, who I co-advise with Dr. Vikash Gaya, also here at Penn State. Joyce worked on this problem for her PhD thesis. She did a fantastic job, and everything that I show is thanks to her, but she did write a lot of papers on this topic, so you can find her papers and read more about all of this work. But my goal today is to kind of introduce the general algorithm and then get kind of like an understanding of how it works, and then look at different applications of that algorithm to different problems. But I won't be going into a whole lot of detail when I get into the application parts. So there are three typical approaches to signal control, and you may know this or not, so I'll just go briefly over them. So the first one is a fixed time approach, where you typically get data from, for example, an intersection on traffic volumes, and you look at the historical data, and based on that data, you try to come up with the best signal timing plan that suits the traffic that you're observing. You can have different kind of signal timing plans for different demand patterns, like a peak morning signal timing and then a midday signal timing, but it's not very flexible. It doesn't really adapt to any of the changes that you might observe. So the next one is a little bit more flexible. It's called an actuated signal timing plan. Is basically the ones where you see, for example, if you are on a minor street and you come there and the signal kind of turns green for you because now it knows you're there, so it introduces your phase into the system. So it can kind of capture these minor variations. It can get to a phase if a car is there and not come to it if it's not there. But it's still, there is quite a narrow range of options that it operates under. The third one that is the most adaptive or the most advanced is called an adaptive one. The adaptive one actually takes into account all the flows that it sees on the roadway from the different approaches, and in real time tries to adjust the signal timing plan based on everything that it's seeing. So it's a little bit more robust to the larger variations in travel demand patterns. It's still narrow in what it can do, but it is the most adaptive signal timing plan that exists today. And it does rely on aggregated information from fixed sensors, so it doesn't really see like individual vehicles. With that being said, we all know connected vehicles are on the rise, and more vehicles have the ability to have some kind of smart system on board, and oftentimes they can actually talk with either each other or with the infrastructure. So they can become a rich source of information to inform the signal timing plan question. We assume that in this scenario, we have vehicles that can talk to a signal time controller and provide their locations and their speeds. And then we assume that the controllers themselves are able to talk to each other as well. For this work, we do not necessarily need cars to talk to each other. We just need them to be able to talk to an infrastructure. So we also need for the infrastructure to be able to talk to the car so that it can provide further information on the signal timings. This helps for speed guidance that can be provided to human-driven or autonomous vehicles and can help make traffic smoother. And I'll get to that later on in the presentation. But first, I will just start with the initial part of the signal timing plan, which is coming up with that signal timing before I talk about providing that information back to the cars themselves. So the goal is to develop a connected and autonomous vehicle-based signal control algorithm that can work under less than 100% CAV penetration ratio, which is probably one of the biggest concerns here, that if we don't have information from all the vehicles, we don't want the system to just not be able to work. We are trying to come up with a solution that works in the intermediate future, so that even if we have, say, 20% of the cars that are out there that can do this kind of communication, we can still come up with a signal control algorithm. The information of connected vehicles is leveraged to identify the non-connected vehicles. I'll show how that's done in a little bit. It can adopt the traditional phasing options. So whatever we have out there, we can use, but we can do this in a flexible sequence. So we are providing more flexibility in that sequence aspect of things. It can provide speed guidance to both human-driven and autonomous vehicles. It can consider multimodal traffic. So I will briefly touch on this. I'll talk about how we can consider buses. I'm going to talk about how we can consider pedestrians.
There we go.
And it can be used to coordinate timings along signalized arterials. So how can you extend this to multiple intersections? But before we get to the arterials, I'm going to start out with a very, very basic intersection. So I'm going to introduce the idea of the control algorithm based on this very simple intersection, which has two roads, one way each. One is going south to north, one is going west to east. But we are going to see that this is going to expand to a more complicated, more realistic intersection. This toy example is just introduced ideas. So the idea is that connected vehicle sends their location and their speed interval to a signal controller at regular intervals, say every 10 seconds. And so in this figure, we have all the vehicles on the roadway. The ones that are connected are in dark blue, are shaded. The ones that are not connected are white. So the dark blue ones tell the signal controller, I'm at this location. I don't know if you're seeing my mouse or not, but it tells them I'm at this location. And then it says, well, my speed is this. So for this car that I'm pointing to, if you're seeing, the speed is 0. For a car further back, the speed is a non-zero value. So this is the initial input that the controller gets. So then the controller uses that input to try to infer some of the non-connected vehicles. And it does that based on stopped vehicles. So it says, okay, there is a stopped connected vehicle at this location, and it's far enough from the intersection itself that it doesn't make sense. It would just naturally stop there. there should be some other cars in front of it. So based on how far that stopped connected vehicle is from the intersection, it infers that there should be 1, 2, 3, X many non-connected traditional vehicles in front of it. So now my algorithm is seeing all of those blue cars, and it's inferring that all of those white cars are also there. So what I have on the roadway is on the left-hand side picture, and what I put into my algorithm, what the input is on the right-hand side picture. You can see that some of those traditional vehicles are in that picture. So my algorithm is taking them into account, but you can see that some of them are missing. The ones that are traveling, that are not stopped. There's one on the west-east approach. There's one on the north-south approach. Both of those are missing from my algorithm. I don't know them. I don't see them. They don't go into any of my calculations. So once I have my input to the algorithm, my goal is to come up with the best signal timing plan. And in an ideal world, I want to come up with the exact departure time of each car so that the total delay is minimized. That is my goal. But if I start going into that, you can see even in this toy example, there is 8 cars. If I try to come up with all the combinations of all those 8 cars and how they can discharge, you can see this is going to become kind of computationally problematic. So rather than looking at those individual vehicles themselves, I start to identify naturally occurring platoons in the traffic stream. I'm not platooning cars together, but I'm just looking at the system to see if I can treat certain groups of vehicles as if they're platoons. And I do this based on the headway or the spacing. So there are basically 2 different types of groups of cars that I'm putting together. One of them are stopped cars. Stopped cars I treat as a platoon. I can identify stopped cars from their spacing. They're pretty close to each other physically. But then there's also some traveling cars that are traveling close enough to each other in terms of time, and I identified those by the headway. So eventually, if I had the input to the algorithm as the middle picture, I platoon some of these vehicles together as the right-hand side picture for my computation. I still retain the information of the individual vehicles, but for my computational parts, I take them in as platoons. So in this figure, you can see I have 2 groups of stopped platoons, the red ones, which are identified based on the spacing criteria. And then I have 2 groups of green platoons, which are identified based on the headway criteria. And those are moving vehicles. You can see that one of these vehicles is far enough from all other cars that it's a platoon on its own. So whenever that happens, I have a platoon of 1 car. So then here is a short video that kind of demonstrates the identification of non-traditional vehicles, and then 2, the platooning process. So you'll see that the yellow cars in this figure are traditional vehicles that don't communicate their information. And the light blue cars are connected cars. When they're rectangles, they are not in a platoon. When they're ovals, they are in a platoon. So just looking at this picture, you'll see yellow cars on the west-east approach that are all rectangles because they're not seen by the algorithm at this point. And then you'll see blue car coming from the west that is a oval. It's in a platoon of its own. And so you'll see that these yellow cars, when a blue car stops behind them, will turn into a platoon. So at this point, if we keep watching, we still have some yellow cars that come. You can see that now all of those yellow cars have stopped on the southbound. And once that blue car stops, all of them turned into ovals, meaning they were platooned with the car behind them, but they were also identified. Now the same is happening on the left-hand side. The blue car stops and the yellow car turns oval, and they pass through the intersection as a platoon. So every time a blue car stops behind a yellow car, you'll see that they all kind of turn an oval shape and they become a platoon that can travel through the intersection together. That's just a brief illustration of how the inputs to the algorithm changes as the system evolves. So then, okay, I have my platoons, great. What do I do with them? I look at all the possible discharge sequences of these platoons to determine my signal phasing and timing plan. So my first step is look at which one of these platoons needs to discharge first from the intersection. Two options, either P1 or P2 are going to discharge first. They're at the front. Once P1 discharges, I have again two options. Either the one platoon behind P1 is going to discharge, P3, or I'm going to switch my signal to the northbound approach, and P2 is going to get the green. So I kind of build this tree based on all the possible options. And if you look at this tree, actually, this is all possible discharge sequences for these 4 platoons. Even for 4 platoons, you'll see there are 6 options. As the number of platoons get larger, this tree grows exponentially. But now that I have my tree, my next step is as I said, I retain the information for all the individual vehicles in these platoons. So I say, okay, if this is my discharge sequence, what will be the delay of each individual car that I see in my algorithm? So for each car that I see in my algorithm, I say for P1, I have this car, it will have delay X, this blue car will have delay Y, this blue car will have delay Z, etc. So I go through the sequence, and based on this sequence, I determine the delay of each car that I know of and calculate a total delay. I do that for each sequence. I look at the values. I say, okay, this one gave me the minimum delay. So I say, okay, that's going to be the order in which I need to discharge these platoons. Once I know the order, I convert that to a signal timing plan. I have here P2, then P1 and P3 and P4. So I know that I have to have a green in the northbound direction for as long as P2 needs to discharge. Again, I estimate how long I think it's going to take for the last car in P2 to cross the intersection and get a duration of the green. And then I do P1 and P3. I say, okay, how long does it need for the last car in that direction to discharge? I get a duration for that green, and then I switch to P4. So that's the final signal timing on the bottom here that I end up implementing. So that's, again, for a very simple issue. So I can do this, like I said, in this enumeration way. And this is a tree where I have 8 options. So now I'm expanding my system to have 2 directions on each approach and left turn is permitted. So with that, I can discharge cars in one of these 8 options. I have like northbound, southbound through, eastbound, westbound through. I can have the northbound, southbound left turns go together, or I could have the northbound through and the left turn go together. So these are all the possibilities. And I'm just trying to enumerate all of my options. And if, for example, I have, let's say I start with this purple one. So once I have my purple starting, I have a left turn phase there. So the left turn platoon discharges. So if I had, for example, the green after that, the left turn for the green is going to have maybe another platoon. But if I had started with the yellow, that left turn platoon would not have discharged. And if I went to green after the yellow, then my green left turn platoon, even though it appears in the second order, the actual cars that discharge would be different. So it complicates the problem having all 8 options. More so than that, if I'm trying to enumerate at each layer, each point gets 8 branches. So at each layer, each point gets 8 branches. This is a subset of the tree. It grows exponentially. It becomes quite complicated to solve. But if we attempt and solve that problem, here is an illustration of how well it can do in terms of delay. Left-hand side, fixed time control. based on the demand, it is a good fixed time control. It's not just a random fixed time control. Right-hand side is the connected and autonomous vehicle algorithm. Because the right-hand side algorithm can adjust to the changes in demand dynamically, it does a much better job of keeping those queues rather short, and the queue never really exceeds more than 5-6 cars in this scenario, whereas you can see relatively larger queues grow on the fixed time control. So this algorithm, even just looking at it visually, is able to perform better than this fixed time control. But the issue is, so far, enumeration has been used, and it's quite computationally costly. So here's a figure showing on the bottom, the x-axis, we have the number of platoons that are enumerated. So, for example, if we only enumerate options for the first 3 platoons, and then we fix the signal timing for the remaining platoons. That's so 3, 4, 5, 6, meaning we're having a larger and larger system that we're enumerating. The orange line shows the average vehicle delay. As expected, as you enumerate more platoons, you can adjust to the demand better. You can lower your delay. The blue line shows the time per control action. As you can see, as you enumerate more platoons, the time per control action grows exponentially. And you can see that even with these 6 platoons, we're at 4.5 seconds of computation time per control action. If I want to implement this in real time, it is not going to be feasible in for larger intersections, higher demands, etc. So we came up with a few solutions. I will briefly walk you through these. Some heuristic methods were identified. So one of them is an intelligent tree search, where at each node, rather than evaluating all 8 options, you only evaluate a subset of options. So here in this example, you only evaluate 3 branches from each node. And you choose those branches. We tried a bunch of different options, but we ended up finding that if we prioritize the platoons with the larger number of vehicles, then we got the best solution. So we chose the 3 largest, the 3 phases, for example, that have the largest number of cars in them for that first platoon, and we only enumerated those options, reducing our tree greatly. We tried genetic algorithm. I'm not sure if and how familiar you are with genetic algorithms, but basically it's an evolutionary algorithm where you create a general population, and each chromosome represents a possible signal timing or phase sequence. We chose to create the genes as phase sequences. So we fixed the length of the chromosome, meaning the number of phases, and we randomly put in phases where you could also have the same phase back to back in this. And then once we have a phase sequence, we again determine the delay, and we did the evolution of the genetic algorithm based on the inverse of the delay. And we mutated the system either with crossovers, where you pick 2 parents, you swap, you pick a point to do the crossover and then swap their information, or random mutation of a given gene or a given phase in this case. Another option was a sequential genetic algorithm. We tried this one because we ended up finding that the most value in a genetic algorithm or in a phase sequence is mostly in the first few phases. So depending on whether or not you choose the first 1, 2, 3 phases correctly, your delays get impacted rather largely. So we said that if we can fix those first 1 or 2 phases at some point in the genetic algorithm, we expected it to perform better. So we came up with the sequential genetic algorithm, where we did a regular genetic algorithm for a certain number of generations, say 30 generations. And after those 30 generations, we said, okay, we look at the best 2 solutions we have, and moving forward, the first chromosome of those first best 2 the first two genes of the best two chromosomes, we fix. We don't allow those to change anymore. And we again run the genetic algorithm for the remaining genes. And then after a certain number, say 45, we fix the second one. So now the first two don't change. Of either you have this first two or this first two, but you can't really change. I don't know if you were seeing that actually. Either you have this first two or this first two. And then after a certain number of generations, you change it again, where you fix the first three and you kind of keep evolving like that. Another option that we tried was a voting recombination, where we said, okay, if a certain phase is appearing in the same position many times, there might be some benefits to keeping that phase there. So we said we'll select a certain number of chromosomes or sequences, and we'll fix a gene or a phase if it appears more than a certain number of times. For example, if it appears more than 3 times in that same position, then we will keep it in that position for future evaluations. If there is no kind of consensus on what phase should appear at that location, then we'll randomly generate that. That was the voting recombination one. And so here is a slide on how those algorithms performed. I'll start with the right-hand side one. The right-hand one side shows the computational effort. On the bottom, I have the penetration ratio of CVs. I'm using that as a surrogate for the number of platoons or the total number of cars that are seen in the system. Because if you have a larger penetration ratio of CVs, you see more cars, which means there are more platoons that you need to evaluate. So even though it says the penetration ratio, you can think of it as kind of number of platoons as well. The red dashed line shows the complete enumeration. Notice that the y-axis is in a log scale. So this is the log of the time per control action. And you can see that when I do complete enumeration, it grows on the log scale as expected. The intelligent tree search is the blue line. That has a much lower computation time, but you can see that it grows significantly on the log scale. The yellow, gray, and blue ones are the genetic algorithm-based ones, and you can see their computation time is pretty flat, meaning even when the problem gets much larger, we don't anticipate the genetic algorithm run times or control times to change much. So that shows us the complete enumeration, very computationally expensive genetic algorithms. They do what we need them to do in terms of computation time as expected. The left-hand side now shows us, okay, good, we know the computation time, but how about their operational performance? So the left-hand side shows us the operational performance, and you can see that the red dashed line, which is the complete enumeration, basically gives us the global minimum as expected. But the surprising part is that the blue one, the intelligent tree search, even though you're enumerating a much smaller tree, it still pretty much achieves the global optimum. So the intelligent tree search does really well in terms of predicting delay. The genetic algorithm-based ones, not so good, but you can see that the traditional and the sequential GA do fairly well. And the sequential GA is the one that we chose to go with as moving forward for its computational effectiveness and its operational effectiveness. So we kind of, as a mid-ground between these two, we ended up choosing the sequential GA that does a pretty good job of coming close, at least, to the optimum solution. So once we determined our method of solving these things, then we tried a few different problems. So one problem was this issue of providing back speed guidance. So in order to do that, we looked at both autonomous vehicles and human-driven vehicles. And in order to be able to explain my results, I'm kind of going to go through a few definitions here, and then I think it will make sense and when I show my results. So we assume that we have connected vehicles and non-connected vehicles. The non-connected vehicles, we can't do anything about. We cannot give them back information. Out of the connected vehicles, we have autonomous vehicles and human-driven vehicles. Autonomous vehicles all can receive speed guidance. From the human-driven vehicles, we assume that some of them have the capability to receive speed guidance and some of them don't. So we assume that a certain percentage of human-driven vehicles can receive speed guidance in order to smooth out traffic. So again, the idea of speed guidance itself is to help vehicles arrive to the intersection only when they can discharge. So let's assume we have a time-space diagram that looks like this. We have a car traveling at speed v0, and we know that the red phase ends at the black dot up there at the end of that red dashed line. We're trying to get to the car to get to that black dot without stopping at the fastest speed that it can. So on the left-hand side, I have an autonomous vehicle. On the right-hand side, I have a human-driven vehicle. I need to provide them with a certain speed, VD, tell them go at this speed so that they get to that black point without stopping. And the process is pretty much the same for autonomous and human-driven vehicles. The only difference is that I need to account for a reaction time for human-driven vehicles, which I don't account for autonomous vehicles, meaning I assume that an autonomous vehicle, as soon as I tell it to go at a certain speed, it starts adjusting its speed like that. The human-driven vehicle has to kind of process that information for a few seconds, which can delay its reaction. And then I account for its deceleration time to get to what that speed needs to be. So here is what speed guidance might look like. So on the right-hand side, I have the algorithm with the AVs, and you'll see that all the cars on the right-hand side are autonomous vehicles, and you'll see some of them slow down as they approach the intersection, like this car coming from the north, so that they don't actually have to stop. You'll also see that for some of them, it is not an option to slow down. They just would have to crawl at a speed less than like 2 miles per hour, which isn't feasible. So some cars, it's possible to slow down and travel at a slower speed. Some cars, they have to stop anyways, even if we know what the signal timing is going to be. We don't want them to be going at a very slow crawling speed. So we did some simulation runs, and one thing that we did assume was that an autonomous vehicle, if we tell them to go at that blue speed shown on the left-hand side, they're going to go at that blue speed, exactly, match it. Human-driven vehicle, they're not going to adopt that blue speed. They're going to adopt a speed that's a little different, say the orange speed. And then once they adopt the orange speed, they're not going to be able to be exactly at that speed. They're going to have some variation. So they're actually going to drive at that green speed, whereas I told them to drive at that blue speed. So in the simulation, I account for the human-driven vehicle driving at that green speed, even though I gave it the blue speed as the guidance. So then looking at some possible trajectories after I provide speed guidance, on the top-hand side, I have trajectories of cars without speed guidance. In the middle one, I have the trajectories when I provide speed guidance to autonomous vehicles. And the bottom one, I have speed guidance provided to human-driven vehicles. You can see on the top-hand side, especially for the second phase, there's a lot of stops. In the middle one, there's almost no stops except for the first 3 cars that stop, that are kind of too late, would have to slow down too much to get a speed guidance for this phase. But you can see, except for those 3 cars, there's pretty much no stops. On the bottom one, you can see that that 4th car also kind of stops. So that causes a little bit of a delay for the other cars. But for the second phase, you can see most of those cars just kind of slow down and speed up, and they don't really stop. So you can see that with the human-driven vehicles, it's not perfect, but there is still benefits to providing the speed guidance. And that's exactly what our results show. So here is some results. Left-hand side shows the average vehicle delay. Right-hand side shows the average number of stops. The different colors of lines are the different penetration ratios of connected vehicles. And the x-axis is what fraction of those human-driven vehicles are receiving speed guidance. And there are no AVs in this initial set of results. First thing to notice is on the left-hand side, as the fraction of human-driven vehicles receiving speed guidance increases, the delay doesn't change. This is not a surprising result for us because we're not actually changing the signal phasing plan at all. We're just telling cars to go at a different speed, but we do not expect cars to discharge from the intersection at a different time. So we do not expect the speed guidance to reduce delays in that sense. But you can see that as the penetration ratio of connected vehicles increases, the delay decreases, which is again, as expected. We have more information, we provide a better signal timing. And you can see that once I get to that 40%, 60% connected vehicle ratio, I'm not reducing my delay much more after that. So most of the benefits of connected vehicle information is actually obtained at those lower penetration ratios. Let's move on to the right-hand side. So now on the right-hand side, you can see that as I move to the right, my average number of stops are decreasing. That's good sign, because that means when I provide this speed guidance to human-driven vehicles, I'm actually making a change and the number of stops are going down, despite the fact that humans are not actually able to follow my guidance 100%. You can also see that as I have more connected vehicles, I have lower number of stops, which is also expected. So this is for 0% AVs. If I go to 20% AVs, you can see the same trends hold. But if you look at the average number of stops part, you'll see that I'll just do another flip so that you can kind of take another look. The average number of stops are actually slightly lower because of those autonomous vehicles, 20%. But what we ended up finding is that if we compare just 20% AVs to just 20% human-driven vehicles, it's actually pretty similar. So 20% human-driven vehicles receiving speed guidance can have a large impact. Not as good as AVs, but significantly large, that it's a close call there. So then I'll just talk about a few other things. One of them is how to look at the system in terms of equity. So one of the things that we noticed when we had our results was that even though the average delays were low, there were some vehicles that had really, really large delays. So on the right-hand side, you can see that there are a significant number of cars that have delays greater than 100 seconds, going all the way up to almost 240 seconds or 3 minutes, 4 minutes. That doesn't sound right. So we modified our algorithm. We added a constraint that the maximum delay cannot exceed a certain threshold. We ran our algorithm with these thresholds. These are the results. So the left-hand side shows the maximum delay as a function of average delay for different thresholds. You can see that as I'm implementing this threshold, I'm on the left-hand side, I am reducing my maximum observed delay. I implement a threshold of 150, 130, 110, 90. My maximum delay is decreasing. My average delay is barely going up. So that's great. I'm able to actually contain these delays without impacting all the other cars that much. After a while, though, the threshold starts to now increase average delay. You can see your blue curve kind of starts to flatten out, and actually it starts to go back up a little bit. The threshold becomes ineffective. But we measured the equity of the system using a Gini coefficient, and we found that we were able to actually provide a better Gini coefficient by implementing this threshold and make things a little bit more equitable. Two more things I want to talk about before I end my talk today. So the one of them is I mentioned multimodal. We incorporated pedestrians into the algorithm by adding pedestrian phases, basically. So the top 8 phases are the phases that I had considered before. I added 7 more phases that account for pedestrians into my algorithm, and kind of looked at, okay, how can I optimize my signal timing considering pedestrian delays, where you can see the pedestrians crossing in that top left corner, the little black dots walking back and forth are pedestrians, and the cars are kind of shown in a similar way. Just for time's sake, I will move on to the results of that. So we basically ended up finding that by assigning a pedestrian delay weight, meaning in our objective function saying I'm trying to minimize my vehicle delay plus my pedestrian delay weight times my pedestrian delay, I can both reduce my pedestrian delay and my average vehicle delay, and I can find a sweet spot. The green line shows the average person delay, and you can see that it is minimized at a certain pedestrian delay weight, and that pedestrian delay weight actually corresponds to the average car occupancy that we assumed. But there is a sweet spot, and we can actually account for pedestrians rather successfully with this algorithm. We've also extended it to arterials, which communicate with each other. We have basically looked at 3 different algorithms for an arterial. One is a centralized one, where we look at all the intersections, take all of their intersection information together and optimize the system. Another one is a decentralized, where each of the intersections operate independently. Another one is a decentralized, but the intersections send information to each other. And we found that that third option, the decentralized, where we send information to each other, performs the best. It performs slightly better than a SCATS, which is the top of the line one that takes into account information of all cars. And you can see the red line, for example, is our average vehicle delay. The blue line is our average vehicle delay, and you can see that it's always below the average vehicle delay of a SCATS algorithm. So we can always do better for cars in that sense. And the information sharing reduces the number of stops, meaning it kind of provides a coordination along our main arterial direction. Okay, that is all I have to say. This is my contact information if you want to reach out to me and you have any questions, and I'm happy to answer any questions that you might have now. Thank you for your attention.
Well, thank you, Dr. Elgin Guler. That was a great talk. And just to get the conversation started, there is a question on the Q&A. Again, you can you can raise your hand and make the question yourself, or you can write it in the chat and we'll make that question for you. And then one person said that they lost a little bit at the beginning. They arrived a little late, but they said, what kind of sensors of instruments are needed on the existing infrastructure for this type of algorithms to be implemented? Is that some, they say, is that some sort of small sensor like DSRC that can be installed on the roadside, or how would you picture that? And then I will add to that, is that would this ever interact with the existing infrastructure at all?
So that's a good question. So I don't anticipate anything fancy. A DSRC could work. The question would be, the current signal controllers they would have to be like almost adaptive controllers to have the flexibility to implement this. So it might be actually better to kind of start from scratch in that sense, because you do need signal controllers that can fully change the phase sequences. So you might have completely different phase sequences than what you're used to. And actually, that's another question that I often get. Wouldn't this be confusing to drivers? So that's also another question that this arises, because it's so flexible and people cannot anticipate perhaps which phase is coming initially. It could create some confusion as well. But yeah, with a DSRC, you could potentially do this, but it might be hard to actually get it to communicate with the current day traffic controller.
Okay, we have a person, Lama and on the audience has a question, I think you can unmute yourself, and thank you for answering the question.
Hello, Professor. Thanks for this nice presentation. I just have a very quick question. Can you go to slide number 24, where you showed a chart with red dashed for autonomous vehicles and for other, yes, this one. So can you please explain more what are the, what can we conclude from this? Because I thought it was important, but I didn't really understand.
Yeah, for sure. So do you see my mouse when I move it?
Yes.
Okay, so then it's worth doing that. So the reds are the red phases, the greens are the green phases. These blue lines, pink lines, green lines are the car trajectories. And at this point here at location -100, they all have the same speed. They're not, I'm sorry, they don't all have the same speed, but at some upstream location, they all arrive in the same fashion. On the top one, we assume that there is no speed guidance. So cars have no idea what the signal timing is going to be. So they approach an intersection, they stop, and then when it turns green, they pass. The middle one is we give the autonomous vehicles the speed at which they should travel. So you can see this car here, this fourth one, that initially had come and stopped and passed. It's now actually, rather than arriving up there, it slowed down, and without stopping, it was able to speed back up and pass the intersection. And that's because we knew that, okay, at this time, you should be able to pass the intersection. So we gave it speed guidance on how it would be able to pass the intersection at that time. And following that, you can see these following cars also have smaller stopping maneuvers. On this last phase here, you can see almost all vehicles had stopped up here. For this one, they haven't stopped at all. So basically, comparing the blue to the pink, we can say speed guidance did a good job of reducing the stops, even though they all passed the intersection at the same time. Comparing the pink to this light blue, we can see that this car that I had pointed to initially, this fourth car, this one received as a human-driven vehicle, it received speed guidance, but it wasn't quite able to follow it. So it still ended up stopping. So the cars following it also ended up stopping, maybe not as bad as up here as the blue one, but definitely worse than the pink one. But if I look at the right-hand side, now the right-hand side, the last set of cars, these light blue ones look very similar to the pink ones and very different than the dark blue ones. So this last set of cars is where speed guidance actually worked. And I was able to reduce the number of stops for human-driven vehicles as if they were autonomous vehicles. So in the second part of things, it did work. So basically, this is kind of showing that speed guidance sometimes works for human-driven vehicles, sometimes doesn't work as well for human-driven vehicles as compared to autonomous vehicles.
Thank you. That was really helpful.
Thank you.
I have someone raise their hand. Lax, you can go ahead and talk.
Sure. Hello, it's Lax. Thanks for the great presentation. I don't work in this area, so just curious, how about like bus stops, railway crossings, or trucks? Can they all be like taken into account for this analysis, or is it already taken into account?
So that's a great question. Bus stops, I have looked into specifically. So bus stops you can take into account. I have looked into bus stops assuming the buses all were connected. So assuming that the buses actually are connected, you can do quite a great deal actually with an algorithm like this, because you can modify the signal timings. For example, if there's a far side bus stop after the intersection and the bus is stopped there during the green, and cars won't be able to cross the intersection because of that stopped bus, you can actually use that information to switch your signal timing. If there is a bus stopped on the near side during the green Again, you can adjust your green times to kind of account for the fact that there is a near side bus stop that is limiting your capacity or your flow to change your signal timings. So I have done that part of the analysis. Trucks, I have thought about quite a lot. The issue with trucks is that they're slower and they're bigger. So the presence of trucks would impact the most this area of our algorithm, where we say, well, in front of a stopped car, there must be X many cars. But if that's a truck right here, then that could be one truck rather than two cars. So trucks would change the implementation, and I have not done it, but I have thought about it quite a lot. Railway crossings, I'm not sure about railway crossings. I mean, I don't know that you could do a whole lot with a railway crossing, just because you don't really have an alternative when the train is passing. So I'm not sure about that one that much. But buses and trucks definitely change. For buses, you can do good. You can improve the system quite a lot. For trucks, there would be some kind of probabilistic analysis there on determining, assuming there is a truck and changing the length of the vehicle that you're assuming.
Okay, that helps. Thank you.
Welcome.
We have Dr. Lewis Lee raise his hand.
Hi. I was wondering, so one of the main metrics is the frequency of stops. So for a lot of planning, it has become customary to use, speeds and now VMT, especially when things are thought of as like environmentally friendly, reducing VMT. How would you pitch sort of this kind of intervention to a planning board or an MPO or something about reducing frequency of stops, as far as what's the benefit to their goals of that? How would you frame it?
So a lot of the emissions in especially stop and go traffic comes from that stopping maneuver. When you stop and when you speed back up, you have the largest number of emissions. So if you can travel at a constant speed for as long as you can, or you don't have to change your speed as much, or you don't have to stop, that is actually pretty environmentally friendly. So by reducing the number of stops, you do have a benefit to the environment. And I haven't actually quantified it so far, but a lot of the models that you look at for emissions, especially at the trajectory level, have the different emissions for the different speed groups, with around the zero speed, the speed changes having the largest impact. So since you're not going into that zero speed zone with these kinds of trajectories, then you can help reduce those extra emissions and help stop like the stop and go movements as well.
Yeah.
All right, I have Egeman. You can go ahead.
Well, thanks a lot, Professor, for this good presentation. I think you may have mentioned, but I feel like as you increase, like if you would like to coordinate between different intersections, this problem might also run into the same problem that you ran with increasing. So like how much further did you go into like we're coordinating more and more intersections, and how much complicated did it get with even more and more, was my question.
Yeah, so I very briefly touched on that, so thank you for bringing that back up. So far, I've only looked at these problem with 3 intersections. At 3 intersections, when you do a centralized algorithm, meaning you take the information from all approaches here, there's 1, 2, 3, 4, 5, 6, 7, 8 approaches, with the middle ones also. If you take into account all of the cars in this system, and you try to optimize it as a whole, with the current state for these 3 intersections, it's still feasible. You can still do it in real time. But what we have found, to our surprise, was that that kind of an approach didn't actually perform that well. And we think it's possibly because when you're trying to coordinate these three intersections, you're actually reducing the flexibility. So when we try to do each intersection independently, but have them communicate, so this intersection communicate to this one and this one, I am green right now, and you can expect to get X many vehicles from me in either direction, but each controller makes their decisions independently. We've actually found that that provided lower delays and a better coordination measured by number of stops along the arterial. So we found that actually we were able to reduce the number of stops, meaning it probably was giving a better green wave along the main line by simply making decisions independently, but just communicating with each other. So with that in mind, it is possible that you could extend this to a much larger intersection without actually changing the computation time at all, because everything can be done in parallel.
Yeah, well, that's very interesting, actually. Thank you.
You're welcome.
Dr. Guler, I have a couple of questions. When we look at the lower market penetrations, it is possible that one leg of the intersection just suddenly, like you just randomly, you never have a connected vehicle pass through, and then you just have non-autonomous or connected vehicles accumulated. How do you avoid the fact that they just stay there forever, like in your algorithm? And with that, to follow up that question is, are you concerned that this kind of algorithm gives just too much priority to connected vehicles? And is there an equity part that you are considering in your algorithm?
Yeah, so that's a great question. And it's brings up an assumption that I didn't explicitly state. We do assume in these algorithms that the connected vehicles are, if there's a 20% penetration ratio, that is 20% on each approach, meaning like one direction doesn't have more connected vehicles than the other one. If that's not the case, you're absolutely right. There is an issue. We do have still minimum green times and maximum green times. So we do max out our green times every now and then, but there is nothing forcing us to go to a different approach. So it is possible that if the connected vehicles are not evenly distributed on a road network, which I wouldn't say there would be a large number of cases where that would happen, unless for some reason you had a smart corridor where cars were encouraged to travel on and others were not. But it would be kind of, I think, hard to have that large imbalance in connected vehicle penetration ratio on approaches. But as long as there is some kind of more or less equitable distribution of connected vehicles, the algorithm is okay. But even then, as I kind of talked about in these slides, even when we made that assumption, we still had some cars that were waiting quite a long time. You can see these are individual vehicle delays, and these also take into account non-connected vehicles. So probably a lot of these on the high end of the individual vehicle delay were cars that were not seen by the signal controller, so they ended up with large delays. But then by implementing this threshold idea of a maximum delay on the vehicles that you could see, we were actually able to do fairly well on reducing that maximum delay. So we were able to actually reduce the maximum delay, for example, from that 250 to like 90, even 80, 70, by implementing a threshold on our algorithm that said, well, if there is an option that is going to provide minimum average delay, if an individual car is going to have too large of a delay, then you cannot implement it. It's not an option. Pick a different one. So that's kind of how we came up with this figure on the left here that showed that we were able to reduce the maximum delay by implementing that threshold, as long as there was some kind of equitable distribution of connected vehicles.
All right, thank you. And then I think we are running out of time unless anyone has any final quick questions, which I don't see anyone raising their hand. I would just like to thank you from the Department of Civil Engineering and Environmental Engineering in the University of Illinois Urbana-Champaign for being here with us and being us, giving us this interesting talk. So unless, again, if anyone has any final thoughts, I just want to say thank you for your presentation.
Thank you very much. It was my pleasure to present. Have a great rest of your evening or afternoon.
Thank you, everyone.
Bye-bye.